Okay. In this lesson, we're looking at sketching subsets on the complex plane. So essentially what we're looking at is we're looking at sets of complex numbers defined within the complex plane. So we'll be given a locus or a condition that will determine a set of values on the complex plane. Okay, so the best way to look at this is to go through a set of examples, purely because the best way is to understand what the condition is telling you rather than to remember specific approaches for different types of functions. Okay, so we'll look at the first example. Okay, so in this example, it says on the Argand diagram, sketch the subset S of the complex plane where S is equal to Z such that the modulus of Z take 1 is equal to 2. So what is this actually saying? So this is what we have to try to understand. This is saying that we're wanting to look at the set of solutions of Z. We're looking at the modulus of Z take 1, which is a distance, and it's always equivalent to 2. So distance equivalent to 2. So we should be able to realize there that equivalent distance probably suggests a circle. Okay, so we're going to go about solving this. We're looking at modulus of Z take 1 is equal to 2. Now we know that Z is a complex number in the form x plus yi take 1. Now, if we group real and imaginary, we get x take 1 in the real and y in the imaginary. So that's our modulus that we're looking at, and it's equal to 2. Now, modulus is square root of real squared plus imaginary squared. And so if we square both sides, we end up with a circle formula, x take 1 squared plus y squared is equal to 2. So we can see straight away that this has a translation of 1 to the right in the real and of 0 in the imaginary. Circle with a center at 1 plus 0 I, and we have a radius of 2. So this will be nice and easy to sketch from here. So 1, 0 is our center, and a radius of 2 means we're adding 2 and subtracting 2 in each axis. So it means this is 1, 2, and 1, negative 2. This one here is 3, 0, and this is negative 1, 0. Here is our subset of the modulus of Z take 1 is equal to 2. So it's a circle surrounding that center point of 1, 0. Okay, so we'll look at another example. So in the second example, we're looking at a subset, solutions of Z, where the modulus of Z take 2 is equal to the modulus of Z take 1 plus I. So we're saying that there's an equivalent distance between two complex numbers, 2 and 1 plus I. So really, what we're looking at here is on that Argand diagram, here's our real and here's our imaginary. We have the point 2 and we have the point 1, 1. We're looking at a set of solutions that are always an equivalent distance between these 2 points. So we're probably looking at a straight line. So let's look at solving this again. We have modulus of Z take 2 is equal to the modulus of Z take 1 plus I. So this is x plus y I take 2 and x plus y I take 1 take I. So when we group into real and imaginary, we have x take 2 and plus y I. So there's our real and imaginary. And x take 1 in the real and y take 1 in the imaginary, which means we end up with a square root of x take 2 squared plus y squared and we have a square root of x take 1 squared plus y take 1 squared. Now if we square both sides, we end up with x take 2 all squared plus y squared is equal to x take 1 all squared plus y take 1 all squared. So we'll have to expand out these brackets. We've got x squared take 4x plus 4 plus y squared, x squared take 2x plus 1 plus y squared take 2y plus 1. Now x squared's on both sides, y squared's on both sides, and so we're left with negative 4x plus 4 is equal to negative 2x plus 2 take 2y. Now if we rearrange this to isolate y, first of all we can see that everything's divisible by 2, so we've got negative 2x plus 2, negative x plus 1 take y. Now if we add y, add 2x and subtract 2, we get y is equal to x, subtract 2, take 1. Now we've got a linear function that represents the initial condition. So this represents all of the points in that subset where the distance is equivalent to z minus 2 and z minus 1 plus I. So we can see we were correct at the start with our thought process that it's a linear function that is equivalent distance between those two initial coordinates. So if we were to sketch that, this is what it actually looks like. Real and imaginary. The initial point will be 0, negative 1, so negative I initially. And each time we go across 1, we go up 1. So that point here would now be 1, 0. And we can run our line through here that represented by y is equal to x take 1. So hopefully that makes sense, and we'll look at a couple more examples again. So in these examples we've got a difference in terminology. We're saying that the argument is equal to pi on 3. The argument of z plus 3, so it has a translation of 3, is going to be negative pi on 3, and then the argument is less than or equal to pi on 3. So when we're talking about the argument, we're talking about that angle. So when we look at A, it's very straightforward. We're saying that the angle that we're dealing with is pi on 3. So we're saying that the angle must always be pi on 3. So this argument here represents this line z. So it's very easy to see that subset. So it's for every value where the argument is a positive pi on 3, real and imaginary. For part B, we're saying the argument with z plus 3, so that means when we add 3 to z, it will be equal to negative pi on 3. So if we were to sketch negative pi on 3, so this first one is argument of z is equal to negative pi on 3. It would simply be that negative angle pi on 3. But when we look at the argument of z plus 3 is equal to negative pi on 3, that will be a horizontal translation. So a real translation, then shifting that across negative 3. So this would be at negative 3, we have our angle negative pi on 3. So that represents z and z. All right. Now for part C, when we're looking at the argument of z is less than or equal to pi on 3, we're saying that the argument of z are an element between negative pi and pi on 3, including that Now we can't include this negative pi because that also is the same as pi, so it's that upper end. So really, we're looking for a region between those two values. And so when we sketch this out, we've got our real and our imaginary. Our first limit is this pi on 3, and our lower limit is negative pi. So dotted line because it doesn't include it. So that's at negative pi. This is pi on 3. And we're looking at this entire area. So it fits our condition. The argument is less than pi on 3. So that concludes those examples with the arguments. In this next example, we'll look at circular relationships that also have inequalities in them. So in part A, we're looking at this z subtract 2 take I is less than or equal to 3. So less than or equal to 3 means we're looking at a circular relationship where it's less than or equal to that distance. So it's still defined by that radius of 3. We're still defined by the center, which is explained by this locus, the modulus of z take 2 take I. But now we're looking at all values between 0 and 3. So if we start by saying this is x plus iy and subtract 2 plus I is less than or equal to 3, we have x take 2 and we have y plus 1, and now we've got square root of x take 2 squared and y plus 1 squared is less than or equal to 3. And that leaves us with the circle equation x take 2 all squared plus y plus 1 all squared is less than or equal to 9. Okay, so this should be nice and easy to sketch. We've got a center at 2, negative 1, and we've got a radius of 3. So 2, negative 1, the real and imaginary axis. So 2, negative 1. When we add 3, we get 5, negative 1, and negative 1, negative 1. And when we add 3 in the imaginary axis, we get 2, 2. And subtract 3, we get 2, negative 4. So if we draw that limit out and realize then it's every value in here meets a given condition. And there it is. There's our sketch of z take 2 take I modulus of is less than or equal to 3. Okay, so when we look at part B, it's a little bit more complex. We're saying that we're looking at a set z such that 2 is less than the modulus of z is less than and equal to 4. And we're looking at the solutions of z such that it has an argument between pi on 6 and pi on 3, including pi on 3 but not pi on 6. Okay, so it's a combination of both. So let's sketch them both separately. Let's look at this first condition. So remember that this z is just x plus I, y. So as it has no other translations, it's going to be centered at 0, 0. So 0, 0. It has a modulus between a radius of, so radius is between 2 and 4. So here we are at 2 and 4, 2 and 4, negative 2 and negative 4, negative 2 and negative 4. Then we're looking at the solutions between those two lines. Now, as it doesn't include the 2, we should have that as a dotted line. When we look at the second condition, it means we're looking at not including from that pi on 6 up to including pi on 3. So we're looking at this space here. Now, if we overlap both of those, we end up with our subset involving both of the conditions. So it means that we have an argument between pi on 6 and pi on 3. And we have a radius between 2 and 4. And so this space here is a subset of our solutions, not including this lower line or that lower line. And there we have it. So although quite complex, if we break that up into components and then bring it back together, pretty easy to see the outcome. Okay, so last example. Okay, so in this example, we're looking to describe the locus defined by an equal distance from the point z plus 3 and 2 times z take I. Okay, so what we've got is x plus y I plus 3, and it's always going to be 2 times x plus I y take I. So we'll split this into our real and imaginary again. So we've got x plus 3 plus y I, and we've got 2 lots of x in the real and y take 1 in the imaginary. So we have x plus 3 all squared and y squared, and we have 2 lots of square root of x squared plus y take 1 all squared. So if we square both sides, now we have x plus 3 all squared and y squared. We have 2 squared, which is 4 lots of x squared, and we have 4 lots of y take 1 all squared. So now we have x squared plus 6x plus 9 plus y squared, and we have 4x squared and 4 lots of y squared, 4 lots of negative 2y, and 4 lots of 1. So you can see here, straight away, we're going to end up with an equation with squares in the outcome. So let's group it all on one side. We'll have 3 lots of x squared. We'll have 3 lots of y squared. We'll have subtract 8y and subtract 6x. And we have subtract 9 and plus 4 is take 5. Now if we move this 5 across, which will probably be the easiest way to work with this, we end up with 5 is equal to. Now I'm hoping that you can realize that this ends up being a circular function. The x squared and y squared are equivalent there. So we have 5 lots of 3 lots of x squared take 2x, and 3 lots of y squared take 8 on 3y. So 3 lots of x squared take 2x plus 1 squared. Now we've added in 1 times 3, so we'll add that across on the other side. And now we've got 3 lots of y squared take 8 on 3y plus negative 4 on 3. That's half of that, all squared. So it means that's 16 on 9 that we've added in, multiplied by 3, so it's 16 on 3. So we have to add 16 on 3 to the other side. So now we have 3 lots of x subtract 1 all squared, 3 lots of y subtract 4 on 3 all squared, and we've got 16 on 3 plus 9 on 3 plus 15 on 3 gives us 40 on 3. Now we'll have to divide both sides by 3, so now we have 40 on 9 is equal to x take 1 squared plus y take 4 on 3 squared. And we end up with a circle with a center of 1 4/3 and a radius which is square root of 40 on 3. Square root of 40 is 4 times 10, so that means we end up with 2 root 10 on 3 as our radius. Okay, so there it is. There's our circle, center 1 4/3 and a radius of 2 root 10 on 3. So that describes the locus defined by the above statement. So that concludes the lesson. Hopefully that makes sense. Sketching subsets is all about understanding the initial statement and being able to algebraically work out, show that in our Cartesian form is probably the simplest approach.